Okay, you guys, so today we're going to talk about 7.7, the complex numbers. This is kind of a long section because it's covering a bunch of different operations on imaginary and complex numbers. So let's first just kind of see what we're going to cover. We're going to write square roots of negative numbers in form of BI. We're going to add and subtract complex numbers. We're going to multiply complex numbers, divide complex numbers, and raise I to power. So these are probably the harder parts. Oops, let me do that in blue. I prefer blue. This is probably the harder stuff. So let's just kind of go through part A and B, get a little bit of groundwork, and then let's work our way in through multiplying, dividing, and powers of I. So first of all, let's talk about what an imaginary number is. So I know it sounds bad, but imaginary numbers are not fake. They're not make-believe numbers. They're just a different type of number. So previously, when we encountered square roots of negative numbers in solving equations, we would say no real solution or not a real number. So that's still true. The problem is we are now able to figure out how to, how to write those correct answers. So they're still not real. They're still imaginary. Or I should say there's still no real solution or not a real number, but now we actually can say the answer is this imaginary number. So imaginary numbers, which includes the imaginary unit I. So here's what the imaginary unit I is. So basically, when we run into the square root of -1, we're going to call it I. So whenever we see a square root of a -1, we're going to call it I. And then we're going to translate that to more than just -1 to -4 to -7 to negative whatever, square roots. We'll be able to manipulate that to get it to work in the fashion that we want. So the other thing is I squared is worth -1. And if you think about that, if you take the negative square root of 1, or I should say the square root of -1, and you multiply it by the negative square root of 1, you get -1. Just similarly, if you took the square root of 3 times the square root of 3, you would get 3. Okay. So when you're working in the complex plane, you can have situations arise that come up where you have a square root of a negative times a square root of a negative. So let's look at this real quick. Okay. So this is the way the book will have you do it. Sometimes I just kind of jump right to the answer, but what the book says is if you run into the square root of -25, previously we would have said, so if we came over here and we said the square root of -25, we would have said, oh, no real solution, and we would be done. We're no longer allowed to do that. We're now going to say, well, the square root of -25, well, I could rewrite this as -1 times 25. So I could rewrite this as the square root of -1 times the square root of 25 using the product property like we learned in the previous section. This is I and this is 5. So this becomes 5I. Okay, so we come over here. All I did was I used this concept that whenever I see the square root of a -1, I can replace it with an I. I can say that it's worth an I. That's what we're going to define it as. So this is actually 5I. When I see the square root of -32, I can say that this is 32. Oops, you know what? Let me write it over here, just like the other one. So we have square root of -32. Well, this is actually the square root of -1 times the square root of 32. I know 32 is actually 8 times 4. I know that this is actually 4 times 2. So here's a pair of 4s. So this becomes I times 4 square roots of 2. Or the better way to write it, 4 square roots of 2I. Sometimes I've also seen it written like this. Okay, the main thing you want to understand is we don't normally have the I inside the square root. So sometimes I will write it like this, just so there's no misunderstanding that the I is inside the square root. But I believe this is probably the way the book will want it. Okay, so then we have 4 square roots of 2I. Okay. Let's do 121. Well, this one we kind of know. So we have a negative. This negative here is this negative here. And then we know that 121 should be 11. But then because it's negative, I'm going to write -11I. So this is how you can do it a little bit quicker in your head. So if I said, let's say part D, I could say the square root of negative 100, and I could just say, oh, that's 10i, right? Because the negative would be I, and then the square root of 100 is 10, okay? So let's just make sure. All right, everything's looking good. Okay, you guys, so let's move on. So multiplying or dividing as indicated. So here's the thing when you're multiplying, all right? So this is technically I square root of 3 times I square root of 7, right? Because they both have a negative, and then we end up with I squared times the square root of 21, okay? However, we go back up here and it says that I squared is worth negative 1, right? Because I times I would be negative 1. So this will become, let's see here. This will become negative square root of 21. Let me see if there's another way I could think of this. I could have done square root of negative 3 times square root of negative 7. Yeah, you can't do it that way because you would lose track of the fact that they were negatives. So this would be a mistake, I believe, to do it this way. And you would get the square root of 21. So this would actually be a mistake to not account for the negative like that. The only way you could do it that way is if they had said like absolute values or something like that. So let's not do that. I was just trying to see if there's a better way to do it. Okay, so now we know that this is actually the square root of negative 8 over 2, but that is the square root of negative 4, and we know that is 2i, right? Because the square root of 4 would be 2, but there's a negative 4, so it's 2i, okay? Something else to keep in mind that this is only for even roots. So even when the index is an even number, so like the square root, the fourth root, the sixth root. So if I had said the cube root of negative 8, well, that's just negative 2. There's no I necessary. So keep in mind, this is kind of, and I'm not saying it's only with square roots, but that's the most common. Square roots, it could be for fourth roots or sixth roots or eighth roots, but in general, we stick to square roots for the most part, but it could be anything. But just so you're clear, the negative inside of a radical is fine if it's a cube root, a fifth root, a seventh root. We don't need imaginary numbers to deal with that. Because if you come up here, remember, what does a square root mean? So if I said the square root of 4 or the square root of negative 4, I'm supposed to find a way to find a number times itself that would give me negative 4. So I could try negative 2 times 2 would be negative 4, but that's not times itself. Or I could do 2 times negative 2 to give me negative 4, but that's not times itself. So my only choices are 2 times 2 or negative 2 times negative 2. But in both those cases, I get positive 4. I cannot get negative 4 using real numbers. It just won't work. Okay, so that's where this comes into play. That's why we need this, is to deal with those situations where the real numbers just simply can't work. They just will not get us to where we want to go. Okay, so now we come over here and I'm going to do more multiplying down here a little bit after I do adding and subtracting complex numbers. But for now, we were just working with imaginary. So now let's kind of motivate this, or let's move on to complex numbers. So complex numbers, or a complex number, is a number that can be written in the form a plus bi. This is called standard form for complex numbers. A plus bi is kind of how everybody wants us to write our complex numbers, where a and b are real numbers, a is a real number, and bi would be an imaginary number. So what a complex number is telling us is it's a combination of a real portion and an imaginary portion of some number. A lot of the time, the reason they want us to write it in a plus bi form is because it would be very easy to graph. So we could have the real number plane here, or the real number line here, and the complex number line here. So if I had 2 plus 3i, all I have to do is go over 2 reals, right? And then go up 1, 2, 3 imaginaries. So that would be right there. Okay, so we would have our, it's basically, it feels an awful lot like a vector. So that's why they like us to write numbers in standard form like this. I oftentimes think of it like this. I think of this as the real portion. This is just me personally. I didn't get this from a math book. This is just how I think of it. And this is the imaginary portion. Okay, so complex numbers have a real portion and they have an imaginary portion. Okay, and they like you to write it in this way. So if B happens to equal 0, that means that A plus BI is a real number. So think about that. What if I had 2 plus 0I? Well, that would just be the number 2. And what if I had 0 plus 2I? That would just be 2I, right? So what they're saying is that if A or B are 0, you either have a real or an imaginary. However, it's kind of a little tricky thing here. Technically, this is a real number, right? But notice I wrote it as a complex number, A plus BI. So every real number could technically be written as a complex number. So if you wanted to say like, oops, let's say we had like the number 5. I could rewrite the number 5. So right now it's a real, but I could rewrite it as 5 plus 0 i's. And now I just rewrote it as a complex. Okay, it seems kind of on a technicality, but because of that, if this is the reals, if this is the real number plane, like all the numbers you could think of, and we put them in this basket inside of here, made of all the reals that exist, the complex numbers are actually bigger. Okay, the complex numbers are bigger because you can fit all the reals in you can make any real number written as a complex number, but you can't go the other way around. So the complex numbers are actually bigger. The set of complex numbers is actually bigger than the real numbers in terms of cardinality, how big the set is, okay? All right, so let's see here. I don't want to go too deep into that. I just wanted you guys to kind of know that complex numbers is probably, for many of you, the biggest number system you'll work with for a very long time. It's actually bigger than the reals in terms of cardinality, and basically meaning the size of the set, how many elements are in the set. Okay, so sum or difference of complex numbers. So this is actually really nice. We don't have to go through a lot of the rules. I just want you guys to see it behaves very similar to x's and variables. So if I had 2x plus 3x, you guys would say, well, that's 5. Oops, that's 5x. So it behaves similarly with I. So if I said 2i plus 3i, I would get 5i. Okay, so it behaves very similar. Now, what if I said, well, what if I take 2x plus 7 plus, let's say, 5x minus 1? Well, we would say, well, that's 7x plus 6. So we would add the x's with the x's and the non-x's with the non-x's. So we can do something similar with imaginaries. So what if I said 2i plus 7 plus 5i minus 1? So I add the imaginary with the imaginary. Oops, I wrote it backwards, actually. I should be writing it like this. Let's say I do 7 plus 2i plus -1 plus 5i. Okay. So now I'm going to do the real with the real. This would be 6 plus the imaginary with the imaginary, 7i. And this would be my complex number. Okay. So I'm not saying that I is a variable. It's not. We know what I is. It's the square root of -1. So it does not vary. However, its behavior when it comes to combining like terms and working with exponents and things like that, it behaves very similar to a variable in that sense, but it is not a variable. We know what I is. A variable means from problem to problem, it changes its value. It varies depending on the problem. So x in one problem could be 7 and x in another problem could be -2. However, in this case, we know exactly what I is worth. I is worth the square root of -1. So that is not a variable. And in the next problem, it's still going to be worth the square root of -1. So let's kind of pause the video, and I'd like you guys to add or subtract these complex numbers. Okay, so hopefully you unpaused the video and you took the real portion with the real portion and the imaginary portion with the imaginary portion. So we should have ended up with 7 plus 4i. And again, it's in standard form. Let's do the same thing with this one. There is the imaginary with the imaginary. So we have 8 minus 2i. And once again, there's our complex number. Okay, let me just make sure everything's going okay. Let me keep up with my notes. Okay, so adding and subtracting is really not that bad at all. Let's do one more. Let's say that I have 3 plus 5i minus -2 minus 7i. Okay, so once again, I take the real with the, oops, you know what? I better distribute first. So let's do 3 plus 5i plus 2 minus, oops, plus 7i. I just distributed the negative to both of them. So now this will become 5 plus 12i. So once again, nice and easy. So again, adding and subtracting imaginary or complex numbers is really not that bad. You just put the imaginary portion with the imaginary portion and the real portion with the real portion. Okay, so hopefully that's not too bad for you guys. So now let's look at multiplying. Now this requires a little bit more effort on our part, and this is going to come into play a lot. I squared is worth -1. So we're going to use this over and over again when we're multiplying complex numbers. And you'll see why right here. Suppose we have 8i times 7i. Well, that will be 56. Now imagine if that was an x, that would be 56x squared. But it's an I, so it's 56i squared. But what's I worth? I squared is worth -1. So then this becomes -56. And there we go. That's all there is to it. Sorry about that. So let me have you guys try a few more. So let me see how many I have in here. You know what? I want to, let's go down to here. I like to do these. Let's have you guys try this one. And then also I'm going to give you 2 plus 3i times -7i. Okay. And then let's pause the video and have you try these two first, and then we'll kind of graduate on to the next set, the slightly harder set. So go ahead and pause the video, give this one a shot, and then come back and we'll kind of work on it together. Okay, so hopefully you guys distributed. This would be 20i minus 35i squared, but we know I squared is worth -1. So this becomes 20i plus 35, right? Because a -35 times a -1 becomes this. Now this is not in standard form. So we're going to write 35 plus 20i. Remember, we want it in A plus BI form, standard form. This is in general how they want you to write all of your answers in standard form. Okay, so now let's look at this other one. So this would be -14i minus 21i squared, right? All I did was distribute, just coming from the other side. So now let's clean this up. This will become 21 minus 14. 21 minus 14i. And remember, all I did was I said that this I squared right here, I squared is worth -1. So -21 times -1 is plus 21. So we have 21 minus 14i, once again, in standard form. So we're good. All right, so let me have you try this one, but I'm going to write out a few more. Let me have you also do 2 plus 3i squared. And let me have you do 5 minus 2i times 5 plus 2i. You know what? I don't like it right there. Two plus 3i. Okay, so 2 plus 3i quantity squared. And let's do 5 minus 3i times 5 plus 3i. So let's try these three problems, okay? So take what you know about multiplying, what you know about foiling and distribution and everything like that, and try these three without me just telling you how to do all of them, okay? So pause the video and give these three a shot. Okay, so hopefully you distributed this times this, this times this, this times this, this times this. So we should have, what is that, 42 plus 24i minus 21i minus 12i squared. And once again, I clean it up at the end. So we have 42 plus 3i. Now remember, the 12i squared is going to become plus 12 because I squared is negative 1. So this becomes 54 plus 3i. And there is our solution. Let me catch up in my notes real quick. All right. So now this one gets a lot of students. So you really got to be careful of this next one right here. 2 plus 3i quantity squared. Please do not do 4 plus 9i squared. That is not the correct answer. Okay. When you see a squared like this to a binomial, or not a binomial, but something with two terms, what I would always recommend, well, it's a binomial if it's a polynomial, but this is a complex number. So you get the idea, something that behaves like a binomial. So what I recommend is don't be lazy, write it out. What does 2 plus 3i squared means? It means 2 plus 3i times 2 plus 3i. So now I'm going to distribute and I get 4, right? So I did 2 times 2. Now I have to do 2 times 3i. So I get 6i. Now I have to do 3i times 2i. So I get another 6i. And now I have to do 3i times 3i. So I get plus 9i squared. Okay. Let me just double check. Yeah, it looks good. So now this is going to become, right? This is going to become a negative 9. So negative 9 plus 4 would become negative 5 plus 12i. And this is our solution. Okay, so don't be lazy, write it out twice. 2 plus 3i squared means 2 plus 3i times 2 plus 3i. Distribute and then, or FOIL, and then you should get negative 5 plus 12i. Now let's take a look at this last one, okay? Now when I do my distribution, I go 5 times 5 is 25. And then this times this is 5 times plus 3i is plus 15i. And then we go the other way, negative 15i, which is nice. And then we do that times 3i, negative 3i times 3i would be negative 9i squared. So this becomes 25. Now these nicely cancel, and that's because these are called complex conjugates. Remember when you have x plus 2 times x minus 2, this was the difference of squares, the middle terms would cancel. And so you didn't have to account for them when you FOILed. They would always cancel each other out. So we have something called complex conjugates where that happens as well. And kind of the nice thing about complex conjugates is in general, you end up with a real number because this negative 9i squared is going to become plus 9. So we end up with 34. So unlike these where you still have a, and again, I know this is technically a complex number, but the real portion is the only portion left. The imaginary portion actually is 0. Okay, so these are just 3 really good examples of something you might be tested on from the complex number section, okay? And again, the big thing about the complex numbers is now we have ways to solve or find solutions that previously we had to just skip and say, oh, there is no real solution. Now we actually can find solutions. In this case, we're just learning how to work with them and simplify them and everything. But it's to work towards more where we can figure out answers that normally we had to just move past. So in the previous chapter, when trying to rationalize the denominator of a rational expression containing radicals, we use the conjugate of the denominator. Similarly, to divide complex numbers, we need to use the complex conjugate of the numbers we are dividing by. So let's see here. So this is just showing you what I was talking to you guys about is when you have, 2 plus 3i times 2 minus 3i. When they're complex conjugates, this and this will become, a squared, and 3i and 3i will become negative 9i squared, which is actually just 13. Did I do this one wrong, or did I use a different value? Oh, no, that's right. Okay. So they're just trying to put into words right here, into a formula, what I was showing you in the previous example. Okay. So here's the thing. And remember, you want to write it in a plus bi form. So it has to be in standard form. This is obviously not in standard form. Okay. So what we're going to do is we're going to multiply the numerator and the denominator by the conjugate of the denominator. So that would be 4 plus 3i times 4 plus 3i. And remember, we have to do it to numerator and denominator so it doesn't actually change the value of the problem. So the numerator is going to be kind of terrible, to be honest with you. We're going to get 24 plus 8i plus 18i plus 6i squared, all divided by, now the denominator will clean up real nice. So that's 16 minus 9i squared. So now let's simplify our I squares, turn them into negative ones. So that will become negative 6. So that will become 18 plus 26i divided by, now that's actually 25, right? Okay, and now that is still not in standard form. So what we do is we split it like this, like we did in one of the previous sections. We have 18 over 25 plus 26 over 25i. And we do this so we have a plus bi form. Okay, that's why we do it. We want a plus bi. We want standard form. Okay, so that one would be one of the harder ones. Let's try something a little bit that looks more simplistic. So once again, we want this in standard a plus bi form, but it's not in the right form because first of all, the I is in the denominator. So let's fix that. What would cancel an I shouldn't say cancel, what would make an I no longer become imaginary, but would become real? Well, we know that I squared is worth -1, okay? So what I can then do is I can multiply this times I. So when I do that, oh, you know what, let me write it over here. Times I over times I. So when I do that, I get 5i over 6i squared, okay? But we know that this is 5i over 6 negative. So this becomes -5, 6i. Okay, so a lot of, it seemed like a bunch of work just to write it in the correct form. But this, again, they want it in a plus bi form. So again, this is 0 minus 5, 6i. This would be, that's the like technical answer, but this is acceptable. That's in the correct form as well. Okay, let me see what else we got. Let me have you guys over here. Let me give you another one. So let's try to divide and write standard form. So let's say we have 3 over 2 minus 6i. Oh, not 6i. Let's do 2 over minus 4i, like that. Okay. So I'd like you guys to divide this and then write your final answer in standard form, which once again we know is a plus bi form. Okay. So pause the video and give this one a shot. Okay, so hopefully you guys use the conjugate, which would be 2 plus 4i, 2 plus 4i. So now this would equal 6 plus 12i divided by, and again, you guys, all I did was I distributed. And now here we're going to get 4 minus 16i squared. But we know this is 6 plus 12i divided by, now negative 16 times I squared is going to become positive 16. So this is going to become 20. Now the thing is 6, 12, and 20 all have something in common. They all have a 2 in common. So I'm going to factor out the 2. That's going to leave me with 3 plus 6i all over 20. And now I can cancel. This is a 1 and this is a 10. So now we're left with 3 over 10 plus 6i over 10. Oh, you know what? I guess I could have just split it from the beginning. That probably would have saved me a little time. So this is 3 and this is 5. I'm just simplifying here, you guys. So 3 over 10 plus 3 over 5i. So there's another way, another type of problem where you can use the conjugate. Sometimes you have to simplify the fraction when you're done. You could have actually split it from right here. And you would have got 6 over 20 plus 12 over 20i, which would have been divided by 2, would have been 3 over 10 plus divided by 4 would have been 3 over 5i. Same answer, right? No difference between the two. Just a roundabout way to do it. I probably should have done it this way from the beginning, but I wanted to show you guys the factoring step. So just make sure you know how to do conjugates, or just in general, removing the imaginary portion from the denominator when you're dividing. So here's something that I wanted to show you guys. This is kind of a pattern. Not kind of a pattern. This has a cyclic nature. It recycles itself every 4 powers. And here's why. So when you take I, we know that that's worth the square root. Square root of -1 is worth I. But now when we square that, we get -1 equals I squared, right? Because I could square both sides. Okay. Now we do this again, and I could do, let me see what's an easier way to do this. Let's do it this one. Let's say I squared, I cubed, I to the 4th. So we know that this is just I to the 1, right? But I squared we know is -1. But I cubed we know is technically I squared times I, which is actually -1 times I. Oops, can't write for some reason, which is actually -1, -I. I to the 4th is actually I squared times I squared. So this becomes -1 times -1, which would become 1. So that's where we notice that I to the 1st is just I squared is -1, I cubed is -I, and I to the 4th is 1. But what if we kept going? What if we said I to the 5th? Well, I to the 5th is just I to the 4th times I. So that's just 1 times I, which is I. But notice that's the same as I to the 1st. What is I to the 6th? Well, we know that I to the 6th is really just I to the 4th times I squared. But that's really 1 times -1. So that's -1. But once again, we look, that's the same. So this recycles itself every 4. And if you look over here, they did it. I, -1, -I, 1. I, -1, -I, 1. I, -1, -I, 1. It just keeps going. So what you can do is when you're dealing with powers of I, you can just divide the power by 4. And whatever the remainder is, that is the power that you're on. So if I take I to the 53, I can just take 53, divide it by 4. 4 goes into 5 one time, we get 4, right? So we get 13. 4 goes into 13 3 times, we get 12, we get 1. This is the power that we're now on. So this becomes I to the 1, which is just I. So that's all there is to it. That's an easy way. That's a nice way that we can do it. I think your book wants you to do it this way. That's how I do it. The book wants you to try to rewrite the 53 as a power of 4K. So we could do I to the 4 times what power could get me close to 53. So 4 times 13 would give me 52. And then I need one more. So that would be times I. So this is actually I to the 52 times I, which is equal to -I. But again, to me, that seems like a little bit harder because you have to think, it's really the same thing, but I just like this method better, you guys. I would strongly recommend that. This is what's actually happening, right? You're taking I to the 4th and you're doing 13 of them, right? But they're all just 1. So what's 1 times 1 times 1 times 1? 13 times. It's just 1 times I is just -1. Oops. Sorry, that would just be I. Okay. So I prefer greatly to do it the other way where I just divide it. So I'm going to take 17 and divide it by 4. 4 goes into this 4 times. We get 16. We're left with 1. So this is, oh, and actually, you know what? I should do something first on this one. This one, because it's a negative exponent, I should write it as 1 over I to the 17. Okay, and now we have to rewrite this as, how do I say this? I want to tell you what it is in the denominator. So I'm going to take 17 and divide it by 4. Remember, it's in the denominator, so that's actually not good for us because we need our i's in the numerator. So I'm going to say this is 4, 16, 1. So we have a remainder of 1. So this is actually 1 over I to the 1. But we learned that we could multiply this by I times I. And we now have I over I squared, which is I over -1, which is negative I. Okay, so that's how I would do it. The book might show you a different way using the 4K. Either way is fine. I just prefer to do it this way. What if I had I to the 223rd power? All I would do is take 223, divide it by 4, and I'll tell you what we're going to get. So 4 goes into 22 5 times. That leaves us with 23. 4 goes into 23 5 times. That leaves us with 20. That leaves us with 3. So I know that I have I cubed. So this remainder is the power that we're on. However, what's I cubed? I cubed is negative I. And all I'm doing is I'm referring back to this table. I cubed is negative I right there. Okay, you guys, that's kind of it for complex numbers. Obviously, you got to practice this. If you don't work with these often, this is something kind of new. So, feel free to, show up to our meetings and ask me for help. Definitely something you have to practice, though. Thanks for watching, you guys. See you in class.